Yeah, good morning, everyone, and thanks for joining to our webinar on broadband IR combustion diagnostics with QCL frequency comms. My name is Markus Geiser. I'm one of the co-founders of IR Sweep, and I'm here with our head of sales, Florian Eigenmann, be moderating the questions. First, before I jump right in, I want to give just one very brief background slide of IR Sweep, in case you're not familiar with us yet. So we were founded 2014 as a spin-off of ETH Zurich. By now, we are 16 full-time equivalents, and we, in the first years, developed the instrument, which is now called the Iris F1. For the first time, showed it in 2017, and since mid-2018, it's fully commercial. And since then, we're focusing on developing applications like combustion diagnostics and also improving the lasers that drive our systems. We have about half the people in R&D and the other half in applications. That's about the rough split. Today, I want to talk first about the challenges in combustion diagnostics and why we go to this space with our dual-com spectroscopy. Then, in general, about the methods, the advantages of the method, and a little bit about the background, what's different compared to other absorption spectroscopy methods that are around. Then I want to, in particular, talk about results that we achieved in collaboration with Professor Ron Hanson's group at Stanford University, who does a lot of combustion diagnostics, is really expert in the field, and then contrast it a little bit with an entirely different application that uses also the advantages of the QCL dual-com spectroscopy, but in an entirely different way, so that you get a bit of a balanced view of the method, and then end with some system properties, what you can expect if you get such a dual-com spectrometer from IR Sweep. So why is it relevant to offer new methods to combustion diagnostics? Well, what you see here on the right is a picture of a so-called shock tube. It's a machine that is used to simulate a combustion. And what you do is you load the fuel and the mixture that you want to load in there, and then you run a shock wave down the tube until you hit the end wall, and then you generate the conditions through the shock wave that you want to have to do a combustion or a pyrolysis or whatever it is you want to do, and then you want to study this. Drivers are, for example, clean combustion or understanding kinetics, different drivers. But it's a very challenging environment for absorption spectroscopy because, as you can imagine, it happens very fast. So typical timescales there are from microseconds up to one or even a few, but very few milliseconds. So whenever you want to study that, you need a very fast acquisition. In addition, it is a not very exactly repeatable process. So when you run nominally the same shock twice down a shock tube, you probably have slightly different temperature and slightly different pressures. So you have to get all the data that you want in a single repetition of the experiment, and that's what we call a single shot measurement. So you can't stitch together different spectral regions, for example, or you can't do that very well. Also, you typically want to measure many different species or narrowband and broadband species at the same time. So it's good to have at least several tens of inverse centimeters available in spectral range so that you can get your multiple species and multiple spectral features. So the method also needs to be broadband. And as a final requirement, since we're looking at combustion, you have something that emits because it's hot, lots of thermal emission. So you need something with a large optical power so that you can actually transmit through the shock tube and distinguish from your laser light from the background radiation of the thermal emission. We do fulfill those requirements, we think. So first of all, our system is quite fast. It goes down in detection time, minimum detection time, to below a microsecond. Typical data set you see here on the left, that's a few microseconds or below 1 microsecond to a few milliseconds. The second feature is that our system is very bright. So compared to standard FTIRs, we have orders of magnitude higher brightness that you typically find in laser sources, and here on the graph on the left, we include only mid-IR sources, just in case you're wondering. So now, if you want to have a mid-IR laser for analysis, you can use what's available as an external cavity laser. You do get the brightness, of course, because it uses the laser source. But in addition to these sweepable mid-IR laser sources, we offer also the multi-heterodyne detection, which then gives the speed in addition. So the combination of brightness and speed is really unique here. And the third big requirement is the bandwidth, the spectral bandwidth. What's broad depends on who you talk to, but for this application, I think the requirement is really a few tens of inverse centimeters. And we realized that through having a laser which emits several hundred or more than 100 colors at the same time. And then the typical result of such broadband laser emission you see here on the left, it's 60 or a bit more inverse centimeters with a single laser or a single pair of lasers that you get simultaneously. And then if you want to switch application, want to switch spectral range, you can do that. You can remove one pair of lasers from the spectrometer and replace it with another one and entirely move the spectral range where you operate. Now, how does this integrate with a combustion system? This is a picture we took at Professor Farouk's lab in Kaust in Saudi Arabia. Here you see essentially the end of the shock tube, the end wall where the conditions are generated that you want to study. And we here place the spectrometer just next to the shock tube, use a periscope to lift the beam up and then transmit through the shock tube and just put the detection system on the other side of the shock tube. It's a bit different than our typical lab applications where the detection system is also housed inside the spectrometer, and there's just a sample compartment where you put your sample. But this works as well. Now, what's inside the spectrometer? I want to do a brief scientific excursion here. So I talked about frequency comms, and so what is a frequency comm? We have some experts in the audience, but for our purposes here, I would like to limit that for here, a frequency comm is really a source with exactly equidistant emission lines in terms of frequency. Hence the name, the comm, from the comm for the hair. And this is more than just the lines that you would get from a Fabry-Perot cavity, because usually there is dispersion, and here dispersion is 0, so you have exact equidistance of those lines. What sounds like a very simple thing has turned out to be an extremely powerful tool in many scientific applications, and was hence also rewarded with the Nobel Prize 2005. And the one advantage that we want to exploit here is that we have those equidistance, and we use this of the spectral lines, and we use this to map the optical frequencies down to microwave frequencies. How we do that, I'll show in the coming slides. And this allows us to do extraction of all the spectral lines that we have in the laser simultaneously. The power of this tool is shown. I mean, there are many examples. I just had to pick out one. For example, here in the bottom left in this Nature paper, where there are measurements with an accuracy of on the 10 to the minus 18 level done with this type of tool. Nowadays, there is a very wide application range for those comms beyond very high precision measurements. Of course, there are optical clocks. There are now also LiDAR applications, and we want to use those comms now for molecular spectroscopy applications. It's just one of the many applications for this type of tool. So how does it work? We said we have a broadband laser emitting many lines. Now we take one of those. It's a semiconductor chip, a QCL, emitting in the mid-IR. We transmit it through a sample, which is symbolized here by just a few molecules. And because we're in the mid-IR, we're exciting the atomic bonds, the molecular bonds between the atoms, and that absorbs part of the light. And now we put this on a detector. Of course, the detector is not able to just resolve those lines by itself. We need some sort of dispersion, some sort of dispersive element to resolve these individual lines. And this is what we need the second laser for. It's symbolized here as well and combined with the beam of the first laser. And now if we look at what happens with the spectrum, we have those two emission spectra. We overlay them on a single detector, that's what we said. And now if we adjust the lasers such that the mode spacings of the two lasers are very similar, we can bring the optical modes, the pairs of those together, and so close that the difference frequencies at which we see beating frequencies are within the detection bandwidth of our detection system, so typically up to 1 gigahertz. And then on the detector, when we do a Fourier transform on the time domain signal, we see what you see here in the bottom panel. We see, again, a set of lines, and each of those lines corresponds to one pair of laser modes. Now, if we introduce an absorber, that's what we do here, we will absorb part of the intensity of the light, and that, referencing that to the intensities that we had before, allows us to extract an absorbance. Now, it's important to note that we see all those lines simultaneously, and that's why we have spectral and temporal resolution at the same time. So we don't need to sweep anything or scan anything. It's really simultaneous. So I think one of the, I guess we can say, unique advantages of dual-com spectroscopy. I want to take one slide to show different regimes of or different types of comms that are available, because a lot of people that work with comms are familiar with near IR, usually fiber-based comms, and they're quite a bit different than the QCL comms that we are using. So most comm systems operate in a near IR around 6,000 inverse centimeters, can be a bit left or a bit right of that. It's also possible to convert them in the mid IR, but let's leave those complex systems out for now. And these systems have usually a bit different characteristics, which are one main reason for that is they have a long cavity, so they have even more laser lines than we have in the mid-IR, and they're also closer together, so they have a finer sampling and more spectral elements, but doing the heterodyning that I described before then in turn leads to a significantly lower time resolution. It has to, it's just a result of the finer sampling of the comm. Notable people who do this actually also in combustion are Greg Rieker's group at UC Boulder, and also the comms themselves are even now commercially available from companies, for example, like Menlo System, and there are many other researchers and companies that work in that space. In contrast, we have the QCL comms that we work with, and they have much shorter cavities, and they work directly in the mid-IR. So we directly have frequency comms from 1,000 to 2,000, or now even 2,200 inverse centimeters, where we generate a lot of optical power where the fundamental row vibrational modes of the molecules are. In turn, we have fewer spectral elements and not quite as fine of a sampling as you have the fiber comms, but because of that, it's a result of that, we can have a much higher time resolution, which is especially relevant for this application here, but can also be exploited for other applications. An example here of a entity that's active in that space is, of course, IR sweep. And I think one advantage that we have in this space is really that there are commercial turnkey spectrometers available, which I think is not really the case for those near IR systems yet. Parts are commercially available and researchers build them up, but there's no system that you can just purchase and connect to your shock tube or whatever system you want to study. If you want to go deeper, I recommend this review here, which I quote at the bottom, about mid-IR frequency comms. It's a bit old now, but it's a very comprehensive overview. Now to the actual system that we were studying in Professor Hanson's group, and I want to thank him for the collaboration. It's been really a very interesting, I think a very successful campaign as well. And yeah, I'm glad that I can share these results here with you guys. So we basically set up what I showed in the picture before. We have the two frequency comms combined, put it on a reference, the signal on a reference detector that you see on the left of the shock tube, and also a combined beam through the shock tube, and we have a detector after it to look at the transmitted light. In parallel, we also use different laser diagnostics here. that are tuned to absorption lines of the molecules that we're going to be looking at. So we can detect a number of species with our broadband system, and in particular, it's two species. It's propyne here, and that is first pyrolyzing and then oxidizing into water. And for propyne and water, there are now separate diagnostics installed in the form of interband cascade lasers. Now, how does it work, or how do we take our data? So we have a shock wave arriving. That's what I said, and that's what that's what defines the conditions that we want to study. And we start our data acquisition a few milliseconds before the arrival of the shock wave. We call the time before the arrival of the shock wave pre-trigger, and we use this as a background signal. And then as soon as the shock wave arrives and we have the conditions that we want, we continuously measure for more than 10 milliseconds, acquire data, and this is longer than the typical, or longer than a test time in this environment. So we have, in one continuous measurement, we have reference data from before the shock wave to and then cover the whole duration of the experiment. We then average down to 4 microsecond chunks of data. This is simply because it improves the SNR, and usually people don't want to look below 4 microseconds. So this doesn't have to be done, but usually we do it. And that it doesn't have to be done, you see on the very top right, which is just the time domain data that we acquire from our detection system. And you see just the top right panel is one cycle of the time domain signal. It's only 200 nanoseconds long. So really, this is the limitation of time resolution that we can achieve. And then it's just a question of signal to noise versus integration time, where you want to be. Now, if we Fourier transform this time domain signal and do a few other things to it, you see the panel on the bottom right, and this is the set of heterodyne lines that we get in our 1 gigahertz bandwidth detection system. You see many lines, and you see that the intensity is not homogeneously distributed. And this just mirrors or is linked to the intensity of the frequency comps that we use. And that is shown in the insets here in the figure. You see they have high intensities on the left and the right, and a bit lower intensity in the middle. And this will then translate into higher signal-to-noise ratio, where you have more intensity in the actual spectroscopic results. Those you see here. In the top panel, you have a pressure trace and a temperature trace. In the bottom panel, you have absorbance data. You see at small negative, or at the very beginning at minus 200 microseconds, you don't see much absorption. Then you see the shock wave coming in. That's at minus about 75 microseconds. The first absorption, can I show this here? Yes, that appears here. Then the shock wave hits the end wall of the shock tube, is reflected, and then you see here a marked rise in pressure. And this is where you see the absorbance of the propyne emerging. What then happens is that over time, the propyne pyrolyzes, and here, as the radical pool increases exponentially, combustion starts, and you see the broadband absorption feature of propyne disappearing because it pyrolyzed and then oxidized, and you see very narrow horizontal water lines appearing that are then constant in time, and the signature of propyne is gone. So here we do see those two species because they that's what overlaps with the laser range that we have chosen. You see those two rectangles marked in white here and here, where the intensity of the COM lines is the highest. That doesn't mean in between, where we have lower intensity, there is no useful information. I rather think it means that the information that we get for each COM line should be when you do fitting or data interpretation, weighted by the intensities or by the error bars. And you can extract those error bars directly from the data, and then you have a large useful range. You just should assign appropriate weights. Yeah. The specifications of the mixture were 2% propyne, 18% O2, and the rest was argon. So it was diluted in argon. Now, a nice comparison with the other diagnostics is shown here. So I said before, in addition to our dual-com system, there were ICL systems running, one specifically measuring propyne, one specifically measuring water. And you see the dual-com data in bold lines here. So both concentrations were extracted from the same laser system, and then those two dedicated laser systems were the gray one, gray thin line was measuring just propyne, and the blue squares were measuring just water. So two dedicated laser systems, one for each species. And in addition, this was also compared to a model, a theoretical model by the Hanson group that shows in the shaded areas the concentrations we expect. And you see the agreement. I think it's quite a nice agreement between the methods and the theoretical model. And the number and types of species that you can observe, of course, depends on the center wavelength that you choose with your dual-com. In this campaign, there was also done a comparison with a swept laser source, an external cavity laser source, which I find quite interesting. And this was done in the duration in which the propyne was present in the shock. So you see the top panel in gray, the swept laser source, and in blue, the dual-com source. And you see the absorption shape is very similar, but you see nicer, better SNR, signal-to-noise ratio, for the frequency comps or for the frequency comp system. And this is because you have only a very limited amount of time with the external cavity, with the swept source, to cover the spectral range before the conditions in the shock tube change. So you have to tune very fast, which means you, of course, suffer on SNR. And then what you can extract from the propyne feature is essentially the temperature, and this is what you see in the bottom panel. So depending on where the peak is, you can extract the temperature. And for the scanned QCL, you can only do this up to a certain temperature here, shown in black triangles to the left of the plot, whereas with the dual-com system, you can, of course, go to ever shorter acquisition times and cover the whole temperature range that was applicable. And you see from the error bars where both methods fit very well with the regression line. Now the whole shock that I talked about can also be visualized in a video. You see the shock arriving at time 0, so the absorption goes up. It's a broadband absorption. Then over the next 750 microseconds, you see the pyrolysis happen, and as the radical pool increases, you see here a rise in pressure, a rise in temperature, and the oxidation, starts, and you see the propyne absorption disappears, and water lines emerge to prove that the combustion actually took place. Now we talked a lot about high time resolution and how this is important for combustion. Now I want to contrast this briefly with an entirely different application, which is polymer chemistry, where you can also take advantage of a dual-com system, but you use the features or the advantages in an entirely different way, so that you get this with a bit of a different, same thing with a bit of a different view on it. Just 2 slides. So I want to focus on the main things. And the challenge here was to have a very fast UV curable glue that we wanted to observe while it cures. And that was a task given to us by a German industrial glue company, Delo. And the way we did it is we put the glue on an ATR crystal, and then we synchronize the data acquisition with the switching on of the UV light, and then we want to observe how does the thing cure. Of course, this is not a microsecond range experiment. This is more milliseconds to very few seconds. So we don't quite exploit time resolution. Also, spectral resolution is not important here. Usually, these experiments are done with 4 inverse centimeters resolution. So we average our acquired data to that spectral resolution as well. Also, the acquisitions scheme is entirely different. So before I said we have a single shock and a single data acquisition that is 16 milliseconds long that covers the shock, the time before the shock and the time after the shock. Now the acquisition is entirely different. We take many short blocks of data, in this case 1 millisecond long, and we take a few before switching on of the UV light, and then after switching off the UV light, we take many blocks of 1 millisecond length with a repetition frequency of 25 hertz. And by that, we can look at an almost infinite amount of time. We're not limited to the 16 milliseconds with this 25 hertz stepping. The duration of the acquisition and the dead time between the acquisitions can be adjusted basically almost freely according to the requirements of the application. And this is the result. So this is in a different spectral range. This is at 1650 inverse centimeters, because that's where the interesting absorption bands appear for this application. You see, as you turn on the light in the bottom right in the figure, one band appears, another band gets bleached, and you see the different spectra on the left. And you see that the whole process takes place on time scales of sub-seconds or very few seconds. And if you want to see absorbances of a few tens of milliabsorbances in these integration times, it gets really challenging with things like an FTIR. And also here, at the same time, you want to see spectral resolution and some degree of time resolution. And there's in FTIR, there's simply not enough light to get this out at the same time. And of course, the goal here is in the end to improve the glue, because the faster the glue cures, the higher the throughput is in the production processes which involve this glue. Now I want to close with describing a bit of the features of the instrument, in case this sounded interesting for what you're doing. So as a light source in our spectrometer, you have QCL exchangeable sources in there, which are housed under the flap that you see on the left, this gray flap here. So when you choose a spectral range for your initial application, you're not bound to this for the lifetime of the instrument. This can be exchanged. Typically, the output power of such a dual-com system, dual-com source is 50 to 100 milliwatts. It depends a bit on where exactly this is spectrally, the properties of the actual lasers, but it's significant power that can also be exploited to do, for example, transmission measurements in liquids that are otherwise not, for example, FTIR is not permitted to transmit sufficient light through to get any good SNR. The spectral ranges that we achieve are typically on the order of 60 inverse centimeters per exchangeable laser source. And then switching from one spectral range to the other means to get another laser source, switch the instrument off and on again, and let it stabilize again for about 30 minutes or an hour or something like that. I want to mention that when you do exchange the laser source in your system, you don't have to realign the whole system. So when you put in another laser, you switch it on again, you already do see a signal. You may want to maximize it a bit, but that's a matter of 1 or 2 or 5 minutes and not a realignment effort of hours. Center wavelengths, again, between 1,000 and about 2,000 or 2,200 wave numbers. We're always working to improve that. And now the spectral resolution is something which is 0.0003 inverse centimeters. And that is basically only limited by the line width of the laser lines. In contrast, the spectral sampling is 0.5 0.3, now up to 0.16. And that means we have an extremely sharp line every 0 point something inverse centimeters. The spectral resolution is, I think, up to par or even outperforms the highest resolution meter long FTIR. So it's also a feature that might be interesting for different applications than combustion, when you really want to look at only line with limited spectroscopy. Time resolution, we covered that, can be below a microsecond, up to seconds or even minutes when more acquisitions are taken. That can be done by different setups in the data acquisition systems. Now, of course, the noise properties are important. We usually achieve smaller 10 milliOD in 1 microsecond integration time, and smaller than 1 milliOD in 100 microseconds integration time. We can zoom into that a little bit by plotting a zero line for the 1650 laser module that we showed before for the curing applications. So you see that for 100 microsecond integration time, you see the gray line. We have a few milliOD noise. And if we allow 10 milliseconds continuous integration, the noise gets quite low. We offer by now a range of lasers that were mostly customer inspired for different applications. We're ever working to increase the number of available center wave numbers, and the typical bandwidth that we achieve is about 60 inverse centimeters. Some regions are more challenging than others, then the bandwidth is a bit smaller, but it is usually around 60. And if what you're interested in is not listed here, please don't hesitate getting in touch. We can do a lot of different wavelengths. It's often a question of how long does it take. If you're really the only person wanting that wavelength, it gets tough, but we are interested in providing more wavelengths that are useful to customers. One question that we get very often is the intensity distribution of the laser, and I want to address this in the end now very proactively. Does the laser have to have minima in the spectrum? No, it doesn't. This is an example of a 6-micron lasers that's used for protein dynamics measurements usually, and there you see a relatively flat spectrum. You see certain minima where the intensity is almost 0, and in the bottom panel you see that this is basically this is where water lines are. So you have no laser light, but this overlaps very nicely with the water absorption lines. So with QCL comms, you will always have you will never have an absolutely flat power distribution because it's an FM modulated comm. But you don't have to have those minima, and you can have a more or less a power distribution which gives you a good SNR over the whole range of the laser module. And this is also a module that we developed according to customer specs for this particular wavelength range. And we're looking forward to doing this for more ranges that hopefully come out of this discussion, for example. Before we do the Q&A, I want to mention we're at a few conferences. At the moment, ICAFS is running in Auckland. A few others are coming up. So if you're at those events, they're in the next couple of weeks, just approach us. And I'm also, of course, more than happy to take any questions right now. So thanks for joining. And please fire away your questions. And Florian Eigenmann will do the moderation of the Q&A part.
Thanks, Markus. For me, this was very interesting, and I have already a few questions which popped up and which we got in the past. One which is interesting for me as well. I'm an FTIR guy. Why can you do such fast spectroscopy? I mean, you're talking about microseconds. What is the main advantage actually of this technique?
Yeah. So the key is really that in many spectrally resolved methods, you have an element that generates the resolution, which is mechanical. So in an FTIR, it's a moving mirror. In those swept laser sources that we mentioned here before in the presentation, it's a moving grating, and we don't have this. It's really limited only by how, by the intrinsic properties of the lasers, and that those are tailored such that we can really achieve sub-microsecond. So no limitation by moving parts anymore, I think is the short answer. Yeah.
Because this is really interesting, especially that you have this high temporal and spectral resolution, which is, I think, completely new on the market with this technology.
I think most applications that our customers want to do really require or take big advantage of this, because this, I think, is almost unique here. And you have also other possibilities to generate temporal and spectral resolution at the same time, but here we really don't have any moving parts. It's on a single detector. It's quite robust. I think it's a very powerful method.
And then another question which comes up also all the time is you mentioned sampling, or some people speak about spacing.
Yeah.
What limits actually the sampling or the spacing?
Yeah.
You mentioned even something about 0.16.
Yeah, a very important question, I think, especially in field of combustion, where you look at gas phase samples. The question comes up is like, how narrow can the lines of the laser be put together, and that is just linked to the length of the laser chip. Standard at the moment is about 0.3 inverse centimeters, and we are working to reduce the spacing down to 0.16 because it's a demand, especially from the combustion community. This is at the moment a very active development goal for us to achieve 0.16. Because smaller gases, of course, have narrower absorptions, and also if you want to look at lower pressures, this is key. It's not so relevant for people who study liquids or solids, because their feature width is typically much broader.
As you probably know, I just joined recently a GRC conference, and one of the questions which popped up there as well was actually, what is the rule of thumb if specifically if you have like very narrow bandwidth like NO or other gases? What should you look at, for example, when you have a half width of, let's say, 0.15? Has this something to do with the spacing?
Yeah, of course. If you want to sample, thanks for mentioning that. If you want to sample a spectral feature, you have to make sure that you have in the full width, that you can resolve the full width of the full width half max.
That you get at least 1 or 2 points.
Yeah, exactly. Yeah.
Okay.
And you don't have to. I think you don't have to sample all the lines of a molecule that are in the range you're studying. And if you, for example, look at the water example that we had before, we had caught, I don't know, maybe 8 or between 5 and 10 water lines. But I think that's sufficient. You don't need to sample every water line very well. I mean, you see that water appears, and you can catch several species if you catch a few lines of several species, you can still see what's going on. You don't have to very well sample all the absorption lines.
Okay.
Or at least not all the absorption lines, in my opinion. Depends on how good your models are. If you don't know where your lines are, of course, it's good to see all of them. But if you know what you're looking for, I think you're good with a few data points.
So you have actually possibility to sweep them or to tune them a little bit if you want to go to other lines. I mean, sometimes if you don't have a line and you have still the possibility to.
Yeah, that's actually also an important point. So if you have a line that is, if you want hiding between two sampling points, you can tune your laser a bit to cover this. This is not something you can do during a shock, but it is something you can do on slower timescales. And we actually have customers who are doing this, who are continuously sweeping the COM wider than the spacing between the lines. So they fill completely the space between the between the spectral lines, and that means really that you get this full resolution of 10 megahertz over the full range of the COM. Yeah, this can be done. It's not a standard at the moment, but this can be done with the system. Yeah,
Nice.
as we shown, their publication should be submitted quite soon.
Actually, I just checked the questions. There are not a lot of questions coming in at this time, but you still have the possibility to send us an email. There's more like a thank you for the presentation, but Marcus mentioned already we will be, or these days actually, we are at ICAFS, we are at ISSW, we are at ICP in Boulder in end of July, I think. Then we are on the high resolution molecular spectroscopy conference in France. Just go to irsweep.com, www.irsweep.com, or drop us an email. I thank you for your attention.
Yeah, all right. Thank you as well, and yeah, see you at one of those conferences. Bye-bye.